All right, as we finish up our discussion on graph theory and our curriculum as a whole, I want to talk about two very specific problems that deal with graph theory. The first one has to do with the edges, and the second one has to do with vertices. So this is called the Chinese Postman problem, and basically what you're being given is a graph, and it's got weighted edges, and basically you need to figure out what is the minimum weight of a closed walk that covers each edge at least once. So we're going to think of these edges as roads, and the postman has to walk down each road so that he can deliver the mail to each house on that road. And obviously he doesn't want to travel down any road more than once if he doesn't have to. And if he does have to, he wants that road to have like the lowest weight, which in this case might be the distance of the road itself. So that's kind of putting it into perspective as to the practical implications of this problem. So there's a few things that can happen with the graph that you're given. If you have a graph that has every vertex with an even degree, meaning there's an even number of edges leaving that vertex, it's a really easy problem because for every path that leads to that vertex, there's a path that goes away from that vertex. So it's really easy to travel every edge exactly once. Okay, but sometimes you have vertices that have odd degree, or at least some of them, and if you do, they're going to come in pairs, and we know that based on the handshake lemma that we talked about at the beginning of this chapter on graph theory. So there's going to be an even number of odd degree vertices. Okay, so there's either going to be two of them, or four, or none. Okay, so if there's only one pair of vertices of odd degree, what I'm going to do is I'm going to use Dijkstra's algorithm to figure out what the shortest path, or the path of least cost, or the path of minimum weight is between them. So because I know I'm going to have to walk this path twice, and I'd like that path to be as short as possible or as cheap as possible. And then if I have more than one pair of vertices of odd degree, I've got to try all possible pairings of those vertices just to see which combination is going to give me the smallest combined weight out of all the pairs added up together. So I'm going to talk about all three of these possibilities, starting off with the first one where I have every vertex with even degree, and I'm just going to show you how easy it is to draw a graph. Okay, there's really no problem here. You're just going to walk down these roads. Okay, and once you run out of roads, though, you've got to be careful, because remember, you do want this walk to be closed, so you want to end where you started. All right. So I made a mistake last time I did this. So this is my second attempt, and this is where I messed up. I went down that 7 path instead of going around this inner square first, and then I got stuck. So I'm going to take this inner square and then take that 7 path, and now I've gone every edge exactly once. So to figure out the cost of this path, all I have to do is add up all of the edges. That's easy enough. Okay? So now what I'm going to do is I'm going to look at this graph right here. As you can see, a lot of the vertices have even degree, but there are two, namely B and F, that have odd degree. Okay, so I need to figure out the shortest path from B to F. And to do that, I'm going to use Dijkstra's algorithm. I'm going to start at B, and if you remember, what we did was we put a 0 at B, and we boxed it. Okay, and then I looked at every vertex leaving the most recently boxed vertex, and I figured out the shortest path to each of those vertices. So to get to C from B, that would be a cost of 4. Then to get to A from B, that would be a cost of 10. And then to get from B to E, that would be a cost of 9. Okay, and the cheapest of those is getting from B to C. So that's what I'm going to do. All right, then I look at, I just boxed in vertex C, so I look at the vertices leaving C and find the cheapest way to get there. Well, there's only one vertex leaving C, and that is D. So it takes me 4 to get to C, and then 3 more to get to D, so that's a total cost of 7. All right, and that was my only option there. Now, looking at vertices that can connect to D, I've only got this one choice here getting me from D to E. 7 plus 3 is 10, but I've already got a shorter path than that leads me to E, and that is 9. So I'm going to actually take the 9 path to E instead of this 10 one that goes all the way around. Okay, and then we are at E, so I will look at all vertices leaving E. So I've got this one that takes me 9 plus 3 is 12, so that will give me a cost of 12 to get to F. This other one would take me 14 to get to F, not a good idea. And then this one, 9 and 8 is 17, also not a good idea. So it looks like the shortest path to get me from B to F is going to be BEF, because that takes a length of 12 total to get there. So I know I'm going to have to do that twice. So starting anywhere you want to start, this is the tricky part. Let's say I want to start at A. I'm going to go to A, and then to B, and then I have to go from B to F. Okay, and then I can go up to G maybe, then over to H, then down to E, then over to D, down to C, over to B. I'm going to take B to F again. Remember, I have to take that path twice. And then I go all the way back to A, which is where I started. Okay? So the total of that path would be the total of all of the edges. But remember, I've got to count the 9 edge and the 3 edge twice, because I actually traveled it twice to get from B to F. Okay? All right. Now I've got a situation where I've got 4 vertices of degree 3. And I've got 1 vertex of degree 4. So I can pair up these odd vertices as either A and B and C and D, or A and C and D and B, or A and D and B and C. So there's 3 possible pairings of those vertices. And just to save us some time, I calculated the shortest path to get from A to B. That's 8. From C to D, that's 5. And I did the same thing with the pairing of AC and BD. And I also did it for AD and BC. So if I add up these costs of AB and CD, that's going to cost me 13. And then if I use a connection from A to C and B to D, that's going to cost me 14. And this one down here, the 6 and the 8, will also cost me a total of 14. So it looks like my best choice is to go from A to B and from C to D, using the path directly from A to B, and then using the path that goes from C through E to D, using both of those twice. All right, so that is the best way to do it. So what I would do to figure out the total cost is I would again add up all of the edges and add an additional 13, because I'm traveling both of these paths, the 8 path and the 5 path. I'm doing that twice. So that's how you handle these types of situations. Again, it's called the Chinese Postman problem. And if you have any questions, please let me know, and I will see you tomorrow.